Inside, almost every modern automatic transmission is one of the most misunderstood components in automotive engineering: the torque converter. For decades, enthusiasts have called it outdated, inefficient, soft, and inferior to manual gearboxes or dual-clutch transmissions. And to be fair, older torque converter automatics often deserved that reputation. They were slow, they felt lazy, they wasted energy, and they made performance driving feel disconnected. But modern torque converters are very different. Once you understand how they actually work, it becomes clear why so many high-performance cars, luxury vehicles, trucks, and SUVs still rely on them. And despite its reputation, it is one of the most elegant solutions ever created for automatic transmissions. To understand why torque converters exist, we first need to understand a major problem with internal combustion engines. The problem is simple. Unlike electric motors, internal combustion engines cannot sustain torque production from 0 revolutions per minute without stalling. At 0 revolutions per minute, combustion stops. Torque output drops to 0. The engine stalls. That creates a major challenge. How do you connect a spinning engine to stationary wheels without instantly stalling the engine? Manual transmissions solve this with a clutch. The clutch temporarily slips. This allows the engine to keep spinning while the wheels gradually begin moving. It works well, but this solution comes with trade-offs. Clutches wear. Slipping creates heat. Heat reduces durability. This becomes especially problematic in heavy vehicles, towing, traffic, hill starts, and off-road crawling. The more weight involved, the more clutch slip is required. And more slip means more heat and wear. So engineers asked a different question. What if the engine and transmission could be connected without direct friction-based contact? No friction disc? No slipping clutch interface? No direct mechanical coupling? That sounds impossible, but it is not. Instead of connecting engine and transmission mechanically, engineers connected them hydraulically using fluid. At first glance, this sounds absurd. Fluid is slippery. How can liquid transfer meaningful torque? The answer is surprisingly simple: by controlling fluid movement. More specifically, by accelerating fluid and redirecting its energy. That is the foundation of the torque converter. A torque converter has 3 main components: pump, turbine, and stator. The pump is connected directly to the engine. The turbine is connected to the transmission input shaft. The stator sits between them. Imagine 2 fans facing each other inside a sealed housing filled with transmission fluid. When the engine spins, the pump spins. The pump accelerates transmission fluid outward using centrifugal force. That moving fluid hits the turbine blades. The force of the fluid causes the turbine to rotate. That rotation drives the transmission. And just like that, torque is transferred from engine to transmission. No clutch, no direct contact, only fluid. This provides something extremely valuable: slip. And in this context, slip is not a flaw, it is a feature. Slip allows the engine and wheels to rotate at different speeds. This is critical during launch. At idle, the engine is already spinning, but the vehicle is stationary. The torque converter allows the engine to continue spinning while the wheels remain still. This prevents stalling. As throttle increases, fluid movement increases, more energy reaches the turbine. The vehicle starts moving smoothly. That smoothness is one of the defining strengths of torque converter automatics. No clutch engagement shock, no sudden torque spike, no jerky launch. This is why torque converter automatics feel so refined in city driving. At this point, torque converters sound nearly perfect. Smooth launch, no launch clutch wear during normal hydrodynamic launch, excellent drivability. So what's the downside? Efficiency. Because the engine and transmission are not mechanically locked together, some energy is lost in the fluid. The pump can rotate faster than the turbine. That speed difference creates energy loss. Energy loss becomes heat, reduced efficiency, and slower response. This was the biggest weakness of early automatic transmissions. This is exactly why torque converters developed such a bad reputation. Older automatics often felt sluggish, inefficient, and unresponsive. The criticism was justified, but then engineers solved the biggest problem. This is where torque converters become truly interesting. After fluid hits the turbine, it exits in the wrong direction. If allowed to return directly to the pump, that fluid would fight against pump rotation. That would hurt efficiency. So engineers added a third component, the stator. The stator sits between pump and turbine. Its job is to redirect returning fluid. Instead of letting the returning fluid oppose the pump, the stator bends the flow and sends it back in a beneficial direction. This dramatically improves efficiency, but that is not even the most impressive part. At low vehicle speed, something remarkable happens. The stator locks in place using a one-way clutch. When locked, it redirects returning fluid more effectively, improving torque transfer within the converter. This enables torque multiplication at low turbine speeds. Yes, a torque converter can multiply torque at the transmission input, without additional gearing and without increasing engine output. Typical torque multiplication ranges from around 1.8 to 1 to over 2.5 to 1 depending on design. That means the transmission can temporarily receive significantly more torque than the engine itself produces. This is extremely valuable at low speed, especially for towing, heavy acceleration, steep inclines, and crawling. This is one reason torque converters remain dominant in trucks and SUVs. They handle high loads extremely well. This is where the comparison gets interesting. Dual clutch transmissions are excellent under aggressive driving. They shift fast, they feel sharp, they feel mechanical. But they have a weakness: low speed operation. In traffic, a dual clutch transmission behaves much like an automated manual. It still needs clutch slip during launch. That means heat, wear, and less smooth operation. This is why many DCT-equipped vehicles feel less refined in stop-and-go traffic. Torque converters avoid much of this low-speed trade-off. They handle low-speed creeping far more smoothly and typically with less drivability compromise. That is a major advantage in real-world driving. A torque converter avoids much of this low-speed trade-off. As vehicle speed increases, turbine speed gets closer to pump speed. The speed difference shrinks. Fluid flow changes. The stator no longer needs to redirect flow aggressively. At that point, the stator unlocks and begins freewheeling. Now the torque converter behaves more like a fluid coupling. Smooth, efficient enough, but still not ideal. Some slip remains, and for decades, that remained the final weakness, until the lockup clutch. The lockup clutch changed everything. At cruising speed, the transmission no longer needs torque multiplication. It no longer needs hydraulic slip. What it needs is efficiency. So modern automatics engage a lockup clutch inside the torque converter. This creates a direct mechanical connection between engine and transmission. No hydraulic slip, no wasted energy, no major efficiency loss. This significantly reduces the biggest weakness of traditional torque converters. Modern systems can even partially engage lockup earlier and more often than older systems. That significantly improves fuel economy, responsiveness, and thermal efficiency. This is one of the biggest reasons modern automatic transmissions are so effective. Many people still imagine automatics as slow and lazy. That image is outdated. Modern torque converter automatics can shift extremely fast. In some applications, shift times rival or exceed dual clutch systems. Modern torque converter automatics can shift remarkably fast enough that the real-world performance gap to dual clutch systems has become surprisingly small. How? Because the torque converter is only one part of the transmission. Modern automatics combine sophisticated valve bodies, fast hydraulic control, adaptive software, and multiple lockup strategies. The result is a transmission that can be smooth in traffic, efficient on highway, and extremely fast under full throttle. That versatility is difficult to beat. This explains why torque converter automatics remain so common and why many premium and performance vehicles still rely on them. The technology works exceptionally well. Modern torque converter automatics are highly refined systems optimized for real-world performance. So if they are so good, why do enthusiasts still dislike them? Because performance and engagement are not the same thing. Manual transmissions feel direct, dual clutches feel aggressive, torque converters feel smooth, sometimes almost too smooth. They remove harshness, they filter vibration, they soften engagement, and drivers often interpret refinement as lack of excitement. That is understandable. But engineering is about trade-offs. And from an engineering perspective, the modern lockup torque converter is a remarkably elegant solution. Not flashy, not dramatic, just extremely effective. It may not be the most exciting drivetrain technology, but it is far more sophisticated and far more brilliant than most people realize. And that is exactly why torque converters continue to dominate modern automatic transmissions. If you want to understand the engineering decisions behind the systems we use every day, subscribe to Engineering Manual.